Hello everyone, and welcome back for the second video on modeling and optimization. We're starting at number 6. An isosceles triangle has a vertex at the origin and its base parallel to the x-axis. So when people have tried to do this problem in the past, they usually get confused because they think of an isosceles triangle like this, with two legs the same. But this one has its vertex at the origin and its base parallel to the x-axis. So it actually looks like this. It's upside down. So this is the same, and this is the same, and this is the base up here. I know we think of base as being at the bottom, but in this case, this one must be flipped upside down. Its vertices are above the axis on the curve y is equal to 27 minus x squared. So here's my curve. So the y-intercept must be 0, 27. And this red curve is y is equal to 27 minus x squared. So that's how I drew it, but there's lots of ways I could have drawn it. I could have drawn it being super tall and skinny. I could have drawn it really wide and short like that. But what do all these triangles have in common? In every single case, the vertice is right on that parabola. That's going to be the key to doing this problem. So I think it's a little tricky with too many lines there. So I think I'm going to stick with just the one that I drew at first. So this point right here is the point xy. It is also the point x comma 27 minus x squared. We've been doing that a lot this year, trying to think of points as everything that you know about them. And there's still one more thing I know about it, that the area, find the largest area, so the area of a triangle in general is 1/2 base times height. So that's still going to be considered the base, and this is going to be considered the height. But look at that height. What does it correspond with? That height is the y value. And this base is twice the x value, because right there, that distance from here to here is x, and that height from here to here is y. But the base is going to be 2 x's. Even if I had drawn it differently, just to show you that it works, even if I do it differently, on this one, this is the point xy, and this is the height y, and the base again is 2 x's because this is x and then this is x. So it works no matter how I draw it. Really think about that for a minute while I delete my blue one, because this is the key, is making sure you understand how I got these pieces. All right, so let's use our steps that I talked about last class. Step 1, write the equation that you're trying to maximize or minimize. The largest area. Area is equal to 1/2 base times height. Step 2 are the constraints. In this case, my constraint comes directly from the picture. My base is equal to 2 x's. Base is equal to 2x. And the height of my triangle, height, is going to be whatever y you're at. So height is equal to y. 3, use your constraints to reduce your equation to one variable. I didn't quite do that. I still have an x and a y. Really, all I did was change it. So 1/2 base times height. So I still need something else. Do you see a way that we can represent y in terms of x? Right up here. Y is, because we're being bounded by this very specific parabola, y is 27 minus x squared. So keep in mind the purpose of your constraint is to reduce your equation to one variable. I'm going to simplify that. These cancel, and I get 27x minus x cubed. And now I'm going to take the derivative, which is 27 minus 3x squared. I'm going to set it equal to 0 and solve. 3x squared is equal to 27. X squared is equal to 9. X is equal to plus or minus 3. Since x represents a distance, I'm only going to use the positive value. So going back to here, my base is equal to 6, 2 times 3, and my height is y, which is 27 minus the 3 squared, and 27 minus 9 is 18. So I found the base, and I found the height, but that's not what the question asked. Remember, step 6 is to always look back and ask and figure out what the question is asking for. They're asking for the largest area. So area is 1/2 base times height. So I could do 1/2 of 6 and get 3 and have to multiply by 18. Or I could do 1/2 of 18, which gives me 9. And 9 times 6, hopefully you know off the top of your head. There are no units on this, but step 7 would have been to do units. If you had them, we don't. But keep in mind, if there were units, they would be squared. But the largest area is 54. You are not required to write square units. So I guess I didn't take a minute and do this. But again, to understand why this works, this is actually not that step. This is the area for different values of x. So it's some kind of a cubic function that has, I know it crosses through 0, and it has different maxes, a max and a min, depending on what x is. So this is the area as x. So as you make x really tiny, you would have had really skinny triangle like that if x was small. And then there's some x that's going to give you the best possible area, probably similar to what we drew. But then if you make x too big, you're going to get this short and skinny. You'll have a big long base for x, but your triangle, because it's being constricted by this parabola, is going to be really short. So the area is going to go back down. We found the maximum area. So here's a graph of the area equation. And how do we do that? By figuring out where the derivative was equal to 0. That will always maximize or minimize a function. All right, let's do number 7. A carpenter has been asked to build an open box, open means no top, with a square base. The sides of the box will cost $3 per square meter, and the base will cost $4 per square meter. So maybe something like the base has to be made out of a thicker material because whatever you're putting inside is very heavy. Find the dimensions of the box with the greatest volume. Okay, I see it. I see my equation number 1. I need the volume of a box. Don't overthink this. The volume of a box is x times y times z, or length times width times height, whatever makes more sense to you. That can be constructed for $48. That can be. There's my constraint. I only want to spend $48. So this one's a little bit new and different because there's actually 2 things going on, in the sense that I do want to talk about the cost, but the cost is dependent on the surface area. So I need a surface area equation that I convert into a cost equation. Cost depends on surface area, or in other words, material. So what is the surface area of my box? So let's draw it. So it said that it had a square base. We don't know how tall it is. But my surface area is going to be 4 of these XYs. These sides right here, there's 4 of them, and each of them are going to cost me $4 per square meter or $3 per square meter. So this is the area of the 4 sides because one side is XY and there's 4 of them. But the cost of the 4 sides is going to be $3 times that area. Now remember, there's no addition here, so it's just going to be 12xy. You don't multiply the 3 times the 4 and the x and the y. It only gets affected to the thing once. And then my bottom is going to be x squared. So the area of the base is going to be x squared. There's no top. If there was a top, I'd have to do it twice. But the cost of constructing that base is going to be $4 times the area. So 4x squared. What is my total cost? My total cost is going to be the cost of the sides plus the cost of the base, and I'm limited to $48. This is my constraint. This was a lot different than what we've done so far. So 4x squared plus 12xy. The constraint will allow us to change the volume equation, which is our main equation, to only have one variable. Right now it has 3. So the first one I can get rid of is that it's not x times y times z because it has a square base. So fortunately that gets rid of one of them for us. It's x times y for this particular volume, length times width times height. So now the question is, how do we use this constraint to reduce this volume equation to just have one variable? So we're going to use the substitution method. How can you rewrite equation 2 to get one variable alone? So you only have one choice. You really can't get x all by itself because it's squared. So I'm going to get this y all by itself. I'm going to do it down here. So 12xy is equal to 48 minus 4x squared, divide by 12x, divide by 12x. So I'm going to put that right in here. Volume is going to be equal to x squared times y, and I'm going to replace y with 48 minus 4x squared over 12x. I can simplify that a little bit. One of these x's cancels, and I get 48x minus 4x cubed. And I'm going to put them individually over 12. I feel like that's a safer way to make sure that I correctly handle the 12, which is 4x minus 1/3 x cubed. It doesn't look so bad now, right? Looked like it was going to be pretty horrible in the beginning, but this derivative is going to be easy. Now, I just feel compelled to tell you. So why do I have to do the derivative? Because this is some kind of a cubic equation that ends down. So ends down like that. The only point I know on it is it passes through 0. This represents the volume for different x's because I could make my box super flat, or I could make the box super tall with a really small x. So a really small x is going to produce a pretty good volume. I mean, it's going to produce some volume. And a really big x is going to produce some kind of volume. But somewhere there's the perfect x that is going to produce the best possible volume for my 48 bucks. Okay, this is being constrained. This equation was created by the constraint of only having $48 for my building materials. But there's definitely a best volume. Is this a real world problem? Simplified, yes, but the concept of it is extremely real world. So I'm finding this point. And how do I find that point? Well, I have the equation. I could type it into my graphing calculator and use max feature. But derivative is so easy. I take the derivative, 4 minus the 3 and the 1/3 cancel, x squared. I set the derivative equal to 0 because right there the slope of my curve is 0. 2 minus x, 2 plus x. So x is either equal to 2 or negative 2. But it's the base, the length of the base, so it's not the negative 2. So, sorry, I'm going to have to ran out of room a little bit. And so I need to just go back and reread the question. What do they want? Find the dimensions of the box with the greatest volume. So I know that my box is going to be 2, what are we doing? Meters. So my box is going to be 2 meters by 2 meters by, and now I need to figure out how high it is. And this is where I go back to this equation that I used for y. Y is equal to 48 minus 4 times 2 squared over 12 times 2. 48 minus 16 over 24 is equal to, what is that? 32 over 24 divided by 8 is 4/3. 1 1/3 meters. Okay? Or 4/3, whatever you want. So find the dimensions of the box of greatest volume that can be constructed for $48. Step 7 was the units, which I remembered. Let's do another one. Number 8. Find the dimensions of a right circular cylinder of greatest volume. I see the greatest. I already know my step 1 is going to be volume. We already did the volume of right circular cylinder in the last video, so I'm not going to go through it again. Volume is pi r squared h. Ooh, inscribed in a right circular cone. Awesome. Here we go. Here's my cone. Right, remember, just means that it's upright, not, slanty, like a, hat that's starting to fall over. So it's perfectly upright. And let's draw a cylinder inside. I could draw that cylinder inside. Or I could draw this cylinder. Or I could draw one somewhere in the middle. You know the answer is going to be somewhere in the middle, right? Because if you're trying to maximize the volume, you don't want it to be too tall or skinny or too flat and wide. It's somewhere in the middle. We're going to find that perfect spot. So in all 3 of these cases, the radius of the cone is 10. And in all 3 cases, the height of the cone is 24. So I need to come up with an equation that explains these constraints. This is usually the hardest constraint for kids. The key is that when you make this cylinder, think about it as slicing through. It's inscribed, which means it touches at the corners. When you do that, think about it as making a base for a tree, for a Christmas tree. So you either have this tall, skinny tree, right? This tall, thin base, and then here's your little tree on top. And you stuck it on this long, thin base. Or here's your tree on top, right? Because you made a nice wide base for it. You could put your tree up there. Or you made this base. So the cylinder is like a base. Why do I want to do that? Because that green triangle in every case is similar to the big triangle. It has all the same angles and it has a corresponding radius. So the radius of this cylinder is also at the bottom of this triangle. So it's going to be proportional. So 10 is the radius of the overall of the overall cone, and R is going to be the radius of the cylinder. And then 24 is going to be the height of the cone, but it's not going to be the height of the cylinder. This cylinder height is not going to be real. It's not similar. What's similar is the green triangle above. Think about it. Look at this green triangle and then look at the big one. Aren't they the same? Well, not the same, but they're what we call similar, which means they're proportional. This green triangle and the overall one, similar. This cylinder isn't. It's the green triangle that gets left after the cylinder. So that cone on top has a radius of R, and this is its height. How can I represent that? Well, what I really want to know is the height of the cylinder, but they're always going to be related. The height of the cylinder and the height of the cone that I've made on the top is always going to be 24 minus h. That's how they're related. So 24 is the whole thing. So however big I make this cylinder, what's left over is going to be 24 minus h. So this represents the original cone, and this represents the little cone on top, which fortunately has the same radius as the cylinder that's underneath it. So we can use R and then 24 minus h. So that's my constraint. We can reduce that. 5 over 12 is equal to R over 24 minus h. I am going to use this constraint to reduce my equation to one variable. I feel like I'd be better off getting h alone, because if I got R alone, then I'd have to square it. And whatever this is going to come out to be, I don't want to square it. So let's clear the fractions. So I'm going to multiply both sides by 12 and both sides by 24 minus h. I'm a big proponent of clearing fractions. This goes away. And on this side, I get 5 times 24 minus h. And on this side, this cancels, and I get 12r. I divide both sides by 5. 24 minus h is equal to 12 over 5r. And lastly, I'm just going to move it this way because I want the h to be positive. Minus 12 over 5r. It's not pretty, but it is how I would do it. So now I'm going to put that in here. Volume is equal to pi r squared times 24 minus 12 over 5r. 24 minus 12 over 5r. So I actually am going to factor out the 12 because I think that's going to make my life easier. And I'm going to factor out the pi. But otherwise, I actually want to multiply through because I don't want to have to use product rule. This is just a constant, so I don't mind that that's on the outside. But I don't want an r on the outside because then I have a product that would require product rule. So I took out the 12. That leaves me with 2, and I'm putting in the r squared. I took out the 12, which leaves me with 1/5, and I'm putting in the r squared. So now I have r cubed. I wanted to do it this way because I wanted to remind you that taking constants out is kind of nice because then you don't have to deal with them. The derivative is still going to have a 12 pi out front. It totally does not matter. And then this is going to be 4r minus 3/5 r squared. Step 5, set it equal to 0. And again, see, now that constant's not going to matter. 4r minus 3/5 r squared. So I do have to solve that. 4r, this part right here is equal to 0, is equal to 3 over 5r squared. I clear the fraction. 20r is equal to 3r squared. I can get rid of one of the r's, and r is equal to 20 over 3. The question, remember step 6, what is the question? Find the dimensions. So this was good. I needed the dimensions. I don't actually want the volume, but I also need the height. So this cylinder is going to have a radius of, I think I wrote 30 over 3, 20 over 3, and its height, how am I going to get that? I'm going to plug that right in here. So 24 minus 12/5 times 20 over 3 is going to be equal to the height. And that's going to come out to be 8. Step 7 are my units. And in this case, it's inches. This is usually the hardest one for kids. They really struggle with getting this proportion. But remember, the key is it's not the cylinder that's proportional to the overall cone. The little cone that is created by making the cylinder is proportional to the overall cone. It's just like a Christmas tree. If you guys went out and you had a Christmas tree and you found the perfect one, but it was 11 feet tall and you couldn't fit it in your house, what would your dad do? He'd just sit there and say, well, we'll just lop it off. And you'd still have a beautiful tree, but you'd be missing that little part. It would be similar. That's what we're doing. We're lopping off the top at some height, but it's this that's similar. So it's always going to be original cone to little cone. And the height of the cylinder won't actually be in the equation. It'll be 24 or whatever the large cone is minus the height. Okay, we're just going to do one more. A cone. Oh, a cone again. I love cones. A cone with a slant height. So they're referring to this over here is to be constructed. Find the largest possible volume of the cone. So I see it, largest possible volume. What is the volume of a cone? Actually, I don't think we did volume of a cone yet. So the formula for the volume of a cone is 1/3 pi r squared h. If you're in honors, you can write that down. If you're in AP, you must have it memorized. Okay, this is going to sound terrible. I'm going to show you how I memorize it. This is not in any way mathematical. It's just how I remember it. So I can remember this volume really easily because it's a circle at the bottom, like a disk, pi r squared, and then it's a disk all the way up. So if I kept stacking like coasters, disk times h, that would be the volume of a cylinder. Okay, here's my totally non-mathy way of remembering. I think to myself, oh, if I made a cone inside of it, doesn't it kind of look like it's 1/3 of it? So I put a 1/3. I realize that that's just a trick of the eye, but it works for me. So 1/3 pi r squared h. That's the formula. I need a constraint. So this constraint is a little hard to see, but it's because it's a right cone that I can know that this will be h, and this will be r, and r squared plus h squared is equal to 6 squared. So you don't really see it right off the top, but it's r squared plus h squared is equal to 36. So I need to get one variable by itself. Last time, we said it would be easier to get h alone because we didn't want to have to square whatever we got for r. But hopefully you see that in this case, it's pretty nice because we want r squared and we can easily get h squared. I'm actually going to leave it like that. I'm going to replace the r squared with 36 minus h squared. I'm going to simplify that a little bit. 1/3 pi is a constant, so I'm not going to touch it, but I don't want to have to do product rule. So I am going to multiply this part together. Step 3, take the derivative. Sorry, one more time, got to do it. What is this graph? This graph is some kind of a negative cubic function that definitely crosses through 0. And it tells you its volume for different heights. So again, how could I make this? I just made it like that, but I could have made a slant height of 6 and made it tall and skinny. I could have made a slant height of 6 and made it really short and wide. So this height, slant height of 6. This height is everything. So how tall should I make it? Should I make it short? If I make a small height, I'm going to get a small volume. But if I make too big a height, if I make it too tall, even if it has a slant of 6, then I'm also not going to get a good volume. I want something in the middle. And what's true about that point? At that moment, the slope or the derivative is 0. So I'm going to set it equal to, not yet. I didn't actually take the derivative. V prime, make sure you're always labeling your work really carefully. This is a constant. I can leave it on the outside. And because I've multiplied this, I don't have to use product rule. I can just do that. I set the derivative equal to 0. But there's two parts. Either 1/3 pi is equal to 0, which it's not, or 36 minus 3h squared is equal to 0, which must be it. So 36 is equal to 3h squared, and h squared is equal to 12. H is equal to plus or minus the square root of 12, which if you break it down into parts you can do and parts you can't, is 2 square roots of 3. I'm going to eliminate the negative. It's not necessary because we're referring to a height. Find the largest possible volume. So in this next step, I missed a step. I don't know. Stopped labeling them. But in this next step, where was the next step? Oh, this was step 2, the constraint. And then this would have been putting them together, taking the derivative, setting equal to 0. You don't really need the steps anymore. I'm sure you've got the hang of it. So a lot of times people go back now and they find the r, which is not bad. R squared is 36 minus h squared is 12. So r squared is equal to, what is that, 24. And so the volume, which is what they want, is 1/3 pi r squared. Notice I didn't actually take the square root because I knew I was going to want r squared times h, 2 square roots of 3. This will give you the volume. I just want to show you there's another way. Hold on, this is 8. 8 times 2 is 16. So 16 pi square roots of 3. And step 7 is the unit. This is in inches, but this is a volume. So this is cubic inches because this was square inches already because I had squared it times another inches is cubic inches. Another, just to throw it out there, another idea is you don't always have to go back to the original equation. If you've only found h, you can bypass finding r by taking h and going directly to the equation that has the h's in it. So you don't have to find r and then go back to the original. You can just find h and then put it right there in equation number 2/3. Okay, that's it for today. There are still 5 problems left, although honors we're not going to do 14, so you only have 4 left. And we'll do those in part C of this video. Have a great day.